Hello, my name is Brey Tucker. I'm the Senior Industry Manager for Project Delivery at Autodesk, and it's an honor to be here today to celebrate Eastman and the Symposium. And this presentation is the Journey Beyond BIM and the Digital Twin. So our story starts thousands of years ago with a brief history of technological developments and how we build. At a time, the creation of an axe was advanced technology. And it was also fortunate technology. The humans that were around these organic objects that they could then have time to manipulate, understand, study, and start to turn into tools was not something every human had. So it was a regional advantage in that they were able to learn and adapt. And an axe was a critical component for making structures and helping cut down trees and lumber and start to begin to understand architecture. Mud bricks were a similar tool to that of an axe, but of a different region. Trees were not in abundance, but sediments and other types of vegetation were, and a study along riverbanks is what gave humans the first idea that something out of the mud could be turned into a building component. The Saqqara is a great example of this type of building. And interestingly, at this time, this was pre-written language. So this was just a concept of being able to communicate through trial and error and learn how to build. The idea of writing and the idea of capturing language and communication took several iterations. The Sumerian tablet is likely the earliest, but interestingly, this as a technology allowed concepts and ideas to go from person to person, transcend generations. So now knowledge could now be built over time and through many generations of people. Shortly thereafter, math was also a concept that started to come into existence. And one of our most important endeavors as we continue to push forward with technology. But math was critical to being able to understand structural integrity. And with that, having an easier way to distribute information and distribute the learning of concepts like math required another invention, and that was something easier to capture ideas down on. So that was paper. So math, paper, and regional resources were what led to vernacular architecture. And that was the study of certain materials and the way objects came together that performed well in our particular locale. And so now the advantage is that the locale had time with a particular type of materials where aesthetics started to be born, and the recognizable form is what we see as vernacular architecture. The abacus was our first calculator. Calculators are an incredibly important tool to visually understand mathematics, going beyond arithmetic and into even more complex concepts like algebra. Looking at anything with actual calculation required a tool to be able to do that. Simple calculators and the written language led to engineered drawings. And so drawings is a very critical component of understanding the ideas and components of architecture and engineering and distributing them among many people. It allows us to simulate a construction before attempting it. And so saving all of that time, trial and error, to learn how we can build better performing structures. And the pursuit of building architecture or engineering, having drawings and simple calculation being served by simple tools, pencils, pens, straight edges, and paper was enough for hundreds of years. And only one other invention is worth note here, and it's the Dewey Decimal System. And this idea of indexing is an incredible intellectual endeavor that led to many big ideas, as we'll get into in this conversation. The mechanical calculator is an adaptation on the abacus, and it was the first time really large numbers started to be conceptualized and put onto paper. And with this idea, mechanical calculator and paper, that was enough to build the modern world as we recognize it today. In the 50s, there were no computers, but there were large structures, simulated designs, and advanced engineering concepts at play. Shortly thereafter, the computer began to form. And it is a series of calculators and transmissions of electric signals that can yield even more complex ideas and transcend even more generations with the way information can be learned, can be leveraged, and can be applied. Because of this, the technology itself started to get smaller, actually. And so digital calculators were able to now be a much smaller form of tool and much easier distributed among many people. Another really important technology is the graphic user interface. It made the complexities of computer simple, and it led to the birth of many new types of applications. One of them that we recognize, AutoCAD, as computer-assisted design. And this was an evolutionary technology for the practice of architecture and engineering because the actual process, the work, remains largely the same. It's drawings and lines on a piece of paper. It's just that all of the tools are now digitized. The paper is on a computer, and the pens have been replaced with vector lines. Building information modeling came much later, but at the same time, it is a wholly different type of practice. So now the lines and what was formerly pens have now been replaced by a model. And the model can be parametrically controlled, and it can have embedded information. And this changes the notion of what a drawing is, because now the drawing can be part of something much more complex. It can be part of a living digital representation of an actual building. And so the life cycle of that building can now be digitized, going from the initial conceptual design into maintenance and operation. This concept has been depicted many times, and the B. Richards graph is still highly referenced for levels of BIM that we're in today. But the important aspect here is the types of associations that we're aspiring on the higher echelons of the BIM level system. And it's connecting into standards, it's connecting into intelligence and things that can help with lifecycle management. But what does this look like? If we look at level of development and we start to break down how all of these different pieces of the building digital components are coming together, we recognize that it's an index. It's an index of categorization, and it's an index that can start to reference different types of standards. The standards of this world are many, and all of them are just complex indexes, looking at how you can categorize and name, and then associating other things to it, the fourth dimensions and the fifth dimensions of BIM, understanding the time at which it might take to procure a certain assembly and the cost. But at the end of the day, the maintenance systems that operate all of our buildings and structures, they look like this. They're simple interfaces that are looking at very kind of simple calculators for KPIs and performance. And the information required, or the information set that goes into these systems, is a spreadsheet. So the spreadsheet itself is an index of categorization, naming standards, and description standards, all working together to make a depiction of these individual objects. So this puts us at a bit of a crossroads for competing motivations and where to develop and how we're going to move forward. On one hand, we can be more efficient, we can draw faster, we can deliver buildings quicker. But on the other hand, we have this concept of value, having a better approach to the designing of buildings and a more considerate approach in how we impact the world around us. The finance industry has made several attempts to determine the return on investment of a BIM process. And if we look at it purely from an efficiency standpoint, the best ROI is by that of the building owner, because their building is getting simulated far more times digitally before it's attempted to be assembled physically. And then even post-physical assembly, the building has a lot of understanding in terms of its maintenance. It's already been considered for how to replace certain items. But on the rest of the design community and the construction community, it's a tremendous amount of more effort because there's more intellectual content that's being generated as a part of the BIM process. Other concepts for value is understanding a computational approach. And this is actually not much different than a calculator. It still is a calculator, except now what we're calculating is an approach. And we're looking at typologies of design. And thinking about communication in this way, it allows a body of people to build on an idea over time and through generations. Building information modeling in terms of the value that it brings to a set of drawings is that there's this much simpler ability to depict three-dimensional information and relay it back to two-dimensional information and the metadata of that information. So tagging content, understanding that you can view and depict many different complex scenarios within a particular assembly allows a qualitative value that is much more around invention and innovation and greatly enhances the design process because of that. Another complexity that we're seeing in our modern world is that as the internet becomes more ubiquitous, it's simpler and easier to create new types of applications that are small, lightweight, and niche. And the issue that this creates is that now you have many independent applications in a typical organization. And in each edition of a new application, there is a new data complexity problem happening in the background. And so this is creating a new enhancement to the BIM process that's much more considerate of that common data environment and that data schema that brings things together. Another issue that we're seeing is that even in the simplifying and distribution of complex models and data sets, it's getting commentary from people digitized. So the art of conversation and having it categorized, understood, and contextualized within a project, that's also a growing concern because as the buildings themselves become more complex, there's much more conversation required to understand the development of those buildings. So when we look at these systems that are cloud-based, that have large and growing teams now collaborating and understanding how their work is performing per package or per milestone of project delivery, it allows us to question the contract model and how it forms and functions in terms of its data set. And because of that, we're given this opportunity to rethink our calculators. Ultimately, what we're looking for is a better way of picking space and ensuring that the data profile in the background makes sense. Understanding the needs and performance criteria of a building is a holy grail in terms of understanding a data profile and categorizing things either by department, by building type, or by a particular owner's own unique legacy needs. And there are many different things that we can do to start stitching data together and understanding that data can be anything. In this case, we're doing a virtual punch list where as one is making a comment, that voice commentary is being transcribed and geolocated within the model, which allows for data visualization concepts where we can start to think about commentary being very simple. The act of making a voice-based comment is as natural as having a conversation. So that if you were to have hundreds of people go through the simulation and start recording commentary, you would get a very simple to understand demonstration of where the performance criteria may be failing. So these are the underpinning concepts of the common data environment. And the common data environment itself is only getting more complex because it's connecting to more types of information. So when we think about how we want to connect to employee resource planning or for any kind of business intelligence tools, the data schema in the background to connect these things is just becoming richer. So there has to be more consideration in terms of how they're going to connect. So the index system itself becomes a compounding problem if we continue to advance in that way. And the common data environment only has more that it can connect to. Finding information from construction, understanding time delays, sequencing delays, how materials moving around a construction site. There are many more things that can be simulated and understood, especially as we get into robotics and into the design for manufacturing workflows. The manufacturing world has been indexing for nearly 100 years. And to rationalize all of the index systems out there with yet another index system is just going to become an ever more complex problem to solve. And we haven't even tapped into the biggest data sets that's out there, and it's actually capturing reality. And so voxel engines and any other types of technologies that are looking at rationalizing point clouds can start to objectify them, but it needs another data profile to start to understand what these objects are and how that might relate back to a design process. So the design process itself right now is served very well by having simple scans done to do design feasibility, to bring things in, leveraging real-time render engines. But the data profiles in the background are just left unconnected. So it's serving the visual purpose, but not serving that data-centric purpose. So the ISO 19650 approach is to start to create a formal discussion on how information requirements are moved across a project. And even though this is a great endeavor to do, ultimately where we're going is that we have to think about how information is understood, processed, and then organized into simpler methods in which we can distribute them visually. And that's where there are really interesting technologies that are no longer thinking about or leveraging an index system. Instead, they're looking at a graph-based database system. And when graphing information, the ability to append labels and work seamlessly across all of them is something that's really unique because the index system is something that can happen. It doesn't have to happen. And so you can have multiple index systems working congruently. And that is the power of graphing. And graphing allows kind of free-form associations, stringing these things together. And so leveraging a database interface like MongoDB, this is really a brave new frontier because the index system is no longer required. The index labeling is something that can be done. It's a much more advanced evolutionary concept of this. So to conclude, what we're really talking about is how to get all of this information to more simply come together. So what you're looking at now is a tool from Infinotus where I've taken the abstract for this talk that I've given you guys today. And what you're able to start to see is this free-form association and inference technology applying across the abstract. So interestingly, with this type of technology, we're able to start applying meta labels. So in the same way that we thought parametric information and metadata on top of objects needing to work its way back into an index, this challenges that concept because now what we're able to do is think about this information and give it multiple ideas, multiple contexts. We might need that so that we can have multiple master standards, uniformats, code E. We can think about all of these things happening at the same time for multiple outputs. And it frees the BIM process from having to be overly concerned about an indexing system and think more about outputs. And so with that, thank you very much, and looking forward to meet all of you at family sessions and discussion. Cheers.